solving exponential equations. Now, we have already done a good deal of solving exponential equations, so just a little bit of review of the things we've seen already. If we had something where our bases were the same, we learned that we could just set our exponents equal to each other to solve. Or that maybe we were given an equation where the bases weren't the same, but we could rewrite it so the bases were the same. So we would go through and we would rewrite 2 and 8 with a common base. So what base could I use? Yeah, I could go through and write 8 as 2 to the third. So then once my bases were the same, then I could just set my exponents equal to each other, and x is equal to 3. Now, most of us can just look at that and automatically know that the answer would be 3, but we can see algebraically how we could get that as well. So then maybe when I come to a problem that maybe isn't quite as obvious instantly what the answer is, I could still follow that same algebraic process. Like if I'm trying to get 1/2 and 32 to have the same base, what common base could I use? 2, right. So let's rewrite 1/2 with a base of 2. What would that be? 2 to the negative 1. Perfect. And when you have a power raised to a power, multiply. So we get 2 to the negative x on the left. 2 to the what on the right? 5th, right. 32 is 2 to the 5th. So now we can say, okay, my bases are the same, so let's set our exponents equal to each other. So if negative x is equal to 5, what is x? Negative 5. And then we can always plug it back in and check it and see if it makes sense. So if I had 1/2 to the negative 5, that's the same thing as 2 to the positive 5, and of course that is 32. But yesterday we saw in section 3.3 that there were some logarithms that we weren't able to solve. Typically, when we encounter a logarithm, the first thing we do is switch it to an exponential form and solve it as an exponential, right? So like yesterday, we saw something like the log base 2 of 6, where we tried to switch that over and say 2 to the x equals 6, and there was no way to get my bases the same and set my exponents equal to each other. And so we had to counter that in a different way with change of base formula. Same thing is going to happen today, only instead of switching from the logarithmic form to the exponential, we're just starting with the exponential form, but we're starting with an exponential where I cannot get my bases the same. 2 to the x is equal to 7. I can't get a common base there, so then I won't be able to set my exponents equal to each other to solve. So we're going to have to go about this a totally different way. Typically, when we solve equations, we use inverses. If you're trying to get rid of adding something, you subtract something. If you're trying to get rid of multiplying by 5, you divide by 5. If you're trying to get rid of a square, you take the square root. So if I'm trying to undo an exponential function, it makes sense then that I'm going to use its inverse. What's the inverse of an exponential? A logarithmic, right. So we're going to use logs to help us solve our exponentials. All right, so let's look at 2 to the x is equal to 7. If I want to use a log to undo that exponential, there are only 2 log buttons naturally on my calculator, a log and an ln. We saw yesterday how on the new operating system you got a log with an alternate base that helps us out. But technically the 2 buttons that come on our calculator are a log and an ln. So if I'm going to insert a log to undo my exponential and I get to pick any log that I want, I'm going to pick one of those 2, right? Because those are buttons on my calculator. So even though I could put in any log that I want to, as long as what I do to one side I do to the other, it's a legal move, I'm going to insert something that's either a log base 10 or ln, since those are the 2 that are on my calculator. All right, so remember that we have that property that says if you have an exponent, you can move it out in front and multiply it by your logarithm. So let's use that. And now I've undone an exponential, right? Now I just have things that are being multiplied and it's much easier to solve. So how do I get x by itself? Divide by ln2. So if I divide by ln2, ln7 divided by ln2, I can throw in my calculator, and I'll end up with 2.807. And if by chance up here in the beginning, instead of inserting ln, I had chosen to insert the common log, the log base 10, then when I got down here, I would have just gotten log of 7 over log of 2. And we know those are equivalent. If I threw that in my calculator, I'd get the same thing. Now, there's an alternate way that you can do that problem that's a little bit of a shortcut. We said that exponentials and logarithmics undo each other, but remember that in the properties that they gave us for logarithms, they said if you take the log of an exponential where the base of your logarithmic and the base of your exponential are the same, they cancel each other out, right? So if I insert a log with the same base as the base of my exponential, literally they will cancel each other out and leave me just with x. So that whole left-hand side goes away and leaves me with just what I'm trying to get. So that's a big shortcut for us. Then what we're left with on the other side is log base 2 of 7. I'm right back to change a base from yesterday, right? I could write that as log 7 over log 2 or ln 7 over ln 2. Either way, throw it in my calculator, and I'm going to get that same 2.807. So really two different ways that I could do this. It does not matter which way you go. Either one is going to work for you. So here's the deal. There are some of you that you're like, oh, please just give me one way to do every single problem. I want to do every single one the same way every single time. Fantastic. Here's what I would suggest. That you insert ln every single time. It'll work on every single problem. You can do that. The reason that I would choose ln as opposed to choosing the log base 10 is that the majority of the problems that they'll give us, the most common base that we'll see on the problems that we do is a base of e. So if you're inserting ln, you'll get to do the same thing every single time, but half the time you'll still get to do that little shortcut too. All right? If you're one of those people that, oh, please just show me the fastest, easiest way there is to do this. I don't care if I have to do each problem a little bit differently if it means that it's the fastest, easiest way to do it. Then what you'll want to do is you'll want to put in a log with the base that is the same as your exponential. So you're going to have to change it a little bit for every single problem. But if you'll do that, then you'll get to use that shortcut every single time. Okay? So it doesn't matter to me which way you go. I know we kind of have both camps. So you can decide which of those you want to follow. All right? So look at example 2. Doesn't really matter which of those two ideals you want to follow. We're all going to do example 2 the same way. Because if you're doing every single problem the same way, you're inserting ln on both sides. And if you're inserting the log with the same base as your exponential, you would be inserting log base e. And log base e is ln. All right, so ln e, remember we have that property that ln e cancels out. The reason for that is ln e just means log base e. So you're basically saying e to the what equals e to the x. And of course that would just be x. So ln e is going to cancel out. We get to use that shortcut and we'll get x is equal to ln 72. And we can throw ln 72 in our calculator and we've got it. Now each of the exponentials that we have looked at so far, every single one of them, we had the exponential isolated on one side by itself before we started trying to solve. So when I get to this next problem, before I start throwing logs in here and making a huge mess, you always want to simplify any way that you can before you start inserting those logarithms. I need to get the exponential by itself before I start putting in logs. So what do I need to do first? Yeah, let's divide both sides by 3. And we'll have 2 to the x is equal to 14. So I'm going to work out this problem both ways. I'm going to work it out for those of you that are inserting an ln every time, and I'm going to work it out for those of you inserting the log with the base the same as your exponential. You don't need to write both of them down. Just write down the method that you like the best, okay? So ln people, we're going to go through over here and insert an ln on each side. And then those of you that are inserting the log with the same base, of course, we're going to insert a log base 2 on both sides. All right, so if you're inserting an ln on both sides, then we can take our exponent and move it out in front. So that would give us x ln 2 equals ln 14. And to get x by itself, we would just divide both sides by ln 2. And then we can throw this in our calculator to get our answer. If you insert a log base 2 on both sides, Log base 2 of 2 would cancel, leaving you with just x. And then I would need change of base formula here, either log 14 over log 2 or ln 14 over ln 2. Either one going to give me 3.807. All right, look at another one of those. For the next one, they give me 4e to the 2x is equal to 5. What do we have to do first? Divide by 4, right. You have got to get that exponential alone on one side before you start trying to undo it. All right, then how are we going to undo that exponential? ln. So we're going to insert an ln on both sides. So again, like we said, if you're inserting an ln every single time, about half the time you're still going to get to use that shortcut. So in this case, ln e cancels out, and we'll be left with 2x, and then we've got our ln 1.25 on the other side. So how do we get x by itself? Divide both sides by 2, and we can throw that into our calculator. Now be careful when you put that in. That's not ln 1.25 over ln 2. It's not the natural log of 1.25 over 2. It's the natural log of 1.25, that whole quantity then divided by 2. So we just want to practice typing these in correctly. All right, all kinds of craziness going on in example number 4. What do we got to do first? Add 4. We got to get the exponential alone on one side. So we'll start by adding 4, then what? Divide by 2. So let's add 4 to both sides and divide by 2, and now we've got our exponential alone. So let's go both ways. Let's start with, if we're inserting a log with the same base as our exponential, we'd put in log base 3. So the log base 3 of 3 would cancel, just leaving me the exponent 2t minus 5. So now how do I get t by itself? All right, so trying to get t by itself, we'll add 5. And then what? Divide by 2. And the fun part of this is like typing that into your calculator, right? Particularly if you have to use change of base, if you don't have that button on your calculator that allows you to put in whatever base you want, if you have to use change of base. If you're putting this in like maybe on a scientific calculator on a portion of a test or something where you don't have a graphing calculator, what you want to do is do log of 7.5 divided by log of 3, get that answer, then add 5 to that, get that answer, and then divide that whole thing by 2. So again, be sure that you practice typing those in and making sure you're coming up with the right answers. Alright, for those of you that like to put an ln in on each side, we're going to start the same way. We're still going to add the 4 to both sides, and we're still going to divide both sides by 2 so that we're at the same starting point. So add 4 to both sides and divide both sides by 2, and we're at the same starting point, but instead of putting in log base 3, we put in ln. So that then I can take my exponent and move it out in front. So that would be 2t minus 5 times that ln 3 that was still there. And to get t by itself, we'll divide by the ln 3 on both sides. And then same story, we have to get rid of subtracting 5 and multiplying by 2, just like we did on the previous example over here. We're still going to add the 5 and divide by the 2. It's just that change of base is already set up for me. Example 12, it says you've deposited $500 in an account that pays 6.75% interest compounded continuously. How long will it take your money to double? All right, so remember our continuously compounding interest formula that we learned earlier in this chapter. That's A equals PE to the RT. They told me that we are depositing $500. What's 500? That's P. That's our principal, right? So we could go through and put 500 in for P. They told me that my rate was 6.75%. Remember, you're always going to change that percent to a decimal. Don't let it freak you out that it's already got a decimal in it. If you had 6.75, if your decimal was right there, to change from a percent to a decimal, you just still back it up 2 places. So 0.0675 is my rate. I don't know my time. That's what's different about this one. In the past, they would say find the amount you would make over 5 years, and we knew our time. In this case, it says how long is it going to take? The time is unknown. How long is it going to take to double your money? So they're telling me what the final answer, the final amount will be over here. If I start with 500 and I double it, we want to end up with 1,000. Okay? So once I get here, we're back to the same thing we've been doing today, where we can say, okay, I got to get this exponential alone. So let's divide both sides by 500. So divide by 500, and I'll get 2 is equal to the exponential. To undo that exponential, we'll insert an ln on both sides. So ln e drops out, just leaving me with my exponent. And to get t by itself, divide both sides by that 0.0675. Throw this into my calculator, and I find out that it's going to take me a little more than 10 years under those parameters to double my money.